Good afternoon to one and all joined here. We welcome everyone for the third day of FDP on advances in composite materials, manufacturing processes, and optimization techniques. The session speaker, Dr.A Nidhin Raj, Associate Professor, TocH, Institute of Science and Technology. He completed his master's and doctorate degree from Amrita University, Coimbatore campus, and he has published so many papers in international journals and conferences. Now, I would like to invite our speaker to share his knowledge in this session. Nidhin, sir.
Yeah. Om Sadgurubhyo Namah. Good afternoon, one and all. I welcome all to this program, FDP, and first of all, I would like to thank the coordinators of this program for inviting me to deliver this talk. Today, I would like to talk about the solutionizing temperature influence on the morphological and general mechanical characteristics of aluminum, silicon, magnesium, nickel, that is particularly A356 alloys. So this was a work which was carried out under my guide, Dr. Sellamuthu, and I had the opportunity to work with such a legend who has published like over 500 papers in this area. Yeah. So just a small overview of what I'm going to talk today. So I will be touching the introduction, then the experimental procedure part that was carried out, and then about the results and discussion, which will include the microstructural analysis of developed alloys, a detailed discussion on the microstructure, and then the hardness part, then tensile properties, that is ultimate tensile strength, yield strength, and percentage elongation, and then about ductility, and then fractography analysis, and finally impact strength analysis also. That is ISOD test that I have carried out here. Then conclusions and then references. So this will be the structure of my presentation here today. So saying a few words about the work initially, this work emphasizes on the mechanical and morphological characteristics of hypoeutectic alloys with a range of solutionizing treatment temperature. Now, moving on to the introduction part. So A356 alloys are used in a vast variety of applications nowadays, like in making boat hull, then for making cylinder linings, then for making other lightweight applications. Anywhere in lightweight applications, you can use, you can go for aluminum always. So A356 alloys particularly has found a huge amount of application in this lightweight application areas. Now this T6 or T7 conditions, that is a particular kind of heat treatment condition that is applied to the base A356 alloys. So that conditions, T6 or T7, that is usually applied for A356 alloys for getting better performance, as well as for getting better property values. Now this determination of an appropriate solutionizing temperature becomes a basic as well as a critical factor as far as the properties of this A356 alloy that is concerned. Okay. Now moving on, these aluminum alloys, basically they are well known for their low weight ratio, low strength to weight ratio actually, and this cast aluminum alloys, they are capable of producing cost-effective products due to the low melting point, when compared to the wrought aluminum alloys, the wrought aluminum alloys that we usually see. Now, the usually used aluminum alloy system is aluminum silicon system. So hypoeutectic alloy system means a compound which has a silicon content less than 13%. So that is why it is called hypoeutectic. Now, if it is greater than 13% silicon, we will call it as hypereutectic. Okay. Now, the silicon content usually varies from 4 to 13% here, and this provides the good casting characteristics. Actually, silicon the presence of silicon actually improves the fluidity of the metal. So having better amount of silicon is better for the casting purpose, or the you'll have better fluidity for the cast. Now, in addition, this addition of silicon enhanced the properties of the base alloy, and that made them capable of being used in automotive sector, transportation, and for manufacture of air or gas cylinders. So all these areas, you can go for such alloy combinations. Now, the previous writings on this aluminum, magnesium, silicon, nickel hypoeutectic combination, that did not tell us anything about the solutionizing temperature. Okay. So solutionizing temperature was not a factor that was studied on this LM25, that is PACE A356 alloy. So that is why this study was focused on developing the alloy A356, that is mainly with the 3% nickel, and studying the different microstructural characteristics, hardness, tensile strength, ductility, impact strength, etc. So all these properties were additionally studied. Now, we're talking about the condition of like this, the conduct of the experiment. Aluminum, nickel, silicon, and magnesium of necessary weight percentages, they were melted in a crucible. And the cast alloys were then solutionized for 8 hours for from 450 to 550 degrees Celsius. Then it was quenched, and then it was aged for 12 hours at 170 degrees Celsius. This fractography intermediate phase and the elementary compositions of the alloy that was found, and it was observed from the investigation that a rise in the solutionizing temperature caused grain refinement in the developed hypoeutectic alloys. Now, a decrease in the value of hardness that was observed with respect to the rise in solutionizing temperature, and it was also noticed from the study that the value of tensile strength, yield strength, as well as ductility, all those got enhanced with increase in temperature from 480 to 510 degree, and then afterwards that showed a small decline from 510 to 550 degree. Now, this kind of trend was also seen with impact strength also, that is an increase from 480 to 510 degree, and then a decrease from 510 to 550 degrees Celsius. Okay. Now, regarding the melting and casting stage of the experimental procedure, so that is the next point that I want to discuss here. So as I said, aluminum, silicon, and magnesium of high level of purity, they were collected in a crucible, and that was placed inside the chamber of a furnace, that was a melting furnace. Now, 3% nickel, weighed 3% nickel was added to this melt, and that was stirred for a long period of time so that we get a uniform mixture of aluminum, silicon, magnesium, and nickel. All right. Now, this nickel is comparatively a high melting element, so hence we had to stir for quite a long period of time for complete mixing. So only if we have a complete mixing of nickel, we'll have or we'll get the desired properties for the alloy and better strength for the alloy also. Now, pouring of the molten metal was carried out at 760 degree into a preheated permanent mold, that was a metal mold. Now, cast rods of diameter 32 mm and length 156 mm that was obtained from this. 8 rods were obtained like this. Okay, 4 rods we got all on a stretch, and then we had to do it again, pour it again, and then we got 8 rods. Okay. Now, prior to pouring of the molten metal into the mold was preheated to 300 degree. So this was carried out in an oven. Lubricoat, die coat material that was applied onto the cavities of the metal mold. And in addition, the cast rods were machined to a length of 16 mm diameter and 156 mm length again. And the specimens from the machined rods were then used for different characterization techniques and various mechanical and tribological testing purposes. The chemical compositions of the cast rods that was analyzed using spectrometer, that was Arun Mech arc spectrometry. Now 4 spots were captured on the specimen surface and their average was found. And the above process was replicated for all the 7 castings performed in this study. Then afterwards, a field emission scanning electron microscopy, that is FESEM, and energy dispersive spectroscopy, that is EDS. Both of these were performed on all the specimens to confirm the presence of nickel content in the hypoeutectic alloy A356. Okay. Now moving on to the various treatment conditions, that is, yeah. So these were the 7 alloys produced in this study. So basically, alloy 1 refers to LM25, that is base A356 without nickel. Alloy 2 refers to the alloy aluminum silicon magnesium nickel alloy in the as-cast condition. Alloy 3 refers to the combination solutionized at 450 degree. Alloy 4 refers to the solutionized alloy at 480 degree. Alloy 5 refers to solutionized alloy at 510 degree. And then alloy 6 refers to solutionized alloy at 530 degree. And then alloy 7 refers to solutionized alloy at 550 degrees Celsius. Now coming on to the T6 heat treatment conditions, the rods that were produced here that were subjected to heat treatment with a T6 temper. Now this T6 temper is something which comprises of solutionizing, quenching, and artificial aging. Solutionizing, quenching, and artificial aging. So this combination is what is referred to as T6. Now among LM25 alloys, this form of heat treatment was very well common. So we have even a paper which describes that the key parameters that plays a vital role in determining the properties of the heat treated specimens are solutionizing time, temperature, quenching medium, and temperature, then cooling rate, artificial aging, that is time and temperature, etc. Okay, so all these becomes important factors in determining the final properties of the alloy. So the factors like solutionizing time, solutionizing temperature, quenching medium, cooling rate, the artificial aging rate, that is time and temperature. All these things becomes important factors here. Now the reason for solutionizing. The solutionizing was carried out basically to bring the alloying elements optimum hardening solution into the aluminum matrix's solid solution. Now to prevent the risk of partial melting and overheating, the solutionizing temperature was held below the maximum temperature of solid solubility. Now the selection of proper temperature for solutionizing is therefore becomes very, very crucial here. Now, in this study, the alloys were mainly subjected to heat treatment, that is T6, in the order of solutionizing, water quenching, and artificial aging. So that was the order carried out. First, we solutionized, and then we did water quenching, and then it was subjected to artificial aging. Now, all the alloys were solutionized for 8 hours, starting from 450 with increments of 30 degrees Celsius till 510 degrees Celsius. And then increments of 20 degrees Celsius till 550 degrees Celsius. And then these alloys were quenched and was then aged at 170 degrees Celsius for 12 hours. Now, coming on to the next, yeah, this is the picture of the actual heat treated rods, the rods that were obtained after the heat treatment. So the first figure refers to LM25, then second refers to as-cast condition, from third to 7th, we have the alloy solutionized at 450, 480, 510, 530, and 550 degrees Celsius. Okay. Now, the next, I would like to talk about the microscopic examination that was carried out. So, metallurgical microscope, that is Carlsey's microscope, was used here for the microstructural observation. The specimens were machined and mounted for morphological analysis. The specimen preparation was done according to the standard metallographic techniques. The polishing of the specimens was carried out using a liner polisher followed by silicon carbide emery layer of numerous grades. Keller's reagent was used as the etching agent, and in this study an optical metallurgical microscope was used to replicate the micrographs at a magnification factor ranging from 100 to 500x, and the images were collected and registered using a CCD camera with software for image processing Motic Images Plus 2.0. Okay, so these are the specifications of the microscope that was used. Okay. Now moving on to the hardness treatment. Yeah. So hardness for all the alloys were tested, and that was carried out using a Vickers micro hardness tester. Vickers micro hardness tester was used here. Now, the sections were prepared and tested as per standard ASTM E384. The parameters for this test were like an applied load of 100 gram force, a period of 15 seconds. Now, before measuring the hardness, the specimens were polished with a silicon carbide emery layer to achieve a scratch-free surface. Now, 20 measurements on the surface of each specimen were taken at various locations, and their average was found. So this was how the hardness test was carried out using a Vickers micro hardness tester. Now, moving on to the tensile testing phase, the tensile strength of the specimens were tested using a universal testing machine. And the figure shown here that represents the sample dimensions that was used. So the sample was of length 136 mm, diameter 12 mm. And on the right side, you can see the actual samples that were machined from the obtained rods for carrying out the tensile testing. Now, these specimens were prepared as per ASTM E4 standard. The specimens were kept between the jaws, and a load of 3000 Newton at a speed of 1.5 mm per minute was applied. The ultimate tensile strength, yield strength, and ductility values were noted, and the fractured tensile specimens were used to analyze the fractography. Fractography test also I have carried out in this study. Now, the next test that was carried out was impact test, that is ISOD impact test actually. Now, since this is the most economical and quickest method to assess the impact resistance of the test specimens, this ISOD test was carried out. Now, resistance to the impact, that is in joules, that is characterized as a material's ability to absorb energy before breaking actually. Now, in addition, the absorbed energy from the specimen before the fracture helps us to assess the hardness and impact strength, and it can be used to examine the temperature effect of from the ductile brittle on the transition state. Okay, on the transition state. Now, the ISOD test was conducted in the present investigation according to ASTM D25604 standard, which used the pendulum striker to produce an impact on the test specimen. Now, initially, the height up to which the pendulum is raised was used for measuring the energy that the specimen absorbs. Now, the more energy the absorbed, the greater the resistance to impact on the scale. Okay. Now, this figure shows the ISOD effect evaluation schematic diagram. So you can see a pendulum striker here, which is used to test the specimen. So test specimen is also seen there. Now, moving on, these were the weight percentages of compositions of the alloys that were produced. So alloy 1 had a silicon of 6.6 in almost all the alloys, like from 6.6 to 6.7. Except in alloy 6, where we found 6.4, and alloy 3 to 6.4. The magnesium was found to be almost constant between 0.2 and 0.4 in all the alloys, and nickel varied from 2.7 to 3.3. Okay, so 3.3 exactly in alloy 4 and 2.7 in alloy 5. Now, these were the EDS spectrum results for the different alloys. Now, it can be noted from the figure that the value of all the elements in the developed alloys was found to be within a range of plus or minus 0.2 to 0.3 weight% from the normal compositions. And the EDS results endorses the existence of aluminum, silicate, magnesium, and nickel elements in all the alloys produced. Now, XRD pattern analysis was also carried out to confirm the presence of an intermediate phase or the presence of nickel in all the alloys. Okay, so the diffraction pattern that was obtained for different alloys are shown in this figure. So with 3% nickel alloy and solutionized at 450, 480, 510, 530, and 550 degree. Now it is seen from the pattern that the peaks resemble to silicon, aluminum, and Al3Ni. Silicon, aluminum, and Al3Ni. So this was confirmed based on the comparison with JCPDF data cards, mainly numbering 8, 000, 005, 652,869, and 652,418. Now, Al3Ni intermediate phase observed for all the alloys in the current studies found to be in accordance with the XRD analysis conducted by previous studies. Now, hence it can be it was concluded that the Al3Ni phase is forming in all the conditions that are being discussed in this investigation. Now, moving on, here I have shown the microstructural observation of alloy 1. Okay. Now, by performing heat treatment analysis, the as-cast structure is altered by increasing the solutionizing temperature actually. Now, it can be concluded from these figures that a steady separation of dendritic structure along with the coarsening of aluminum grains. Okay. So a steady separation of dendritic structure along with coarsening of aluminum grains is noticed. And when the temperature of the solutionizing is increased, the spheroidization of eutectic silicon has occurred and may also be perceived from the heat-treated alloys. Okay. Now moving on specifically to the microstructural observation in alloy 1, the figure shown here, that is figure A, depicts the rapidly cooled and solidified matrix of LM25 or A356 alloy. And the microstructure depicts a fine interdendritic pattern of aluminum silicon surrounding the bright primary aluminum grains. Okay, the eutectic Mg2Si phase has dissolved and not precipitated in aluminum solid solution because of rapid cooling and absence of aging effects here. Okay. Now the figure B, that is the second figure here, shows the same microstructure at higher magnification of 200x. And the higher magnification shows the morphology of the dendritic bond of aluminum silicon particles clearly. Okay. So that is regarding alloy 1's microstructure. Now moving on to the alloy 2's microstructure. So the figure A here shows the aluminum silicon magnesium nickel as-cast alloy rapidly cooled and solidified matrix. Micrograph revealed the fine interdendritic pattern covering the vivid primary grains of aluminum silicon alloy. Now the eutectic Mg2Si has dissolved here also, not precipitated in aluminum solid solution because of rapid cooling and absence of aging effects. But the large particles of undissolved Al3Ni were dispersed randomly in the aluminum solid solution, as you can see from figure A. Now the same figure, that is figure B, depicts the same microstructure magnified at 200x, and the higher magnification shows the morphology of aluminum silicon as a dendritic boundaries. Now the large Al3Ni lumps which have not dissolved in the matrix can also be seen from figure B. Okay, so that is regarding microstructure of alloy 2. Now moving on, this is the microstructural observation of alloy 3 actually. So aluminum silicon eutectic interdendritic pattern grains in aluminum solid solution, they are depicted in figure A. Now it can be seen from figure A that the eutectic Mg2Si has broken down and emerged at the primary aluminum grain boundaries. Now the other eutectic step of Al3Ni has become round in shape and is existing along with aluminum silicon particles. Now there was no finding of Chinese script-like eutectic particles in the microstructure. And this aluminum grains also appeared as luminous areas. Now the second figure, that is figure B, portrays the same higher magnification microstructure that has settled the grain limits and various precipitates together with aluminum silicon particles. Now figure C depicts the microstructure at 500x magnification, and it highlights the settled grain limits with aluminum silicon, Mg2Si and NiAl3 precipitated eutectics. Now even after following 8 hours of solutionizing, the cast dendritic grains were found to remain considerably. So that was a finding that we got from the microstructural observation of alloy 3. Now moving on to alloy 4, the figure A describes aluminum silicon as massive segregation of fine teeth-like particles here. Now the rest of the eutectic phases of Mg2Si and Al3Ni have gone into and appeared at grain surfaces. Now figure B represents the higher magnification microstructure of the same, that is 200x. In this you can see that some dark Mg2Si eutectic particles precipitates, they can be observed. Now figure C shows the objects at atomic level. Now the size of the brought out object is found to be fine here, okay, in figure C. Now moving on to alloy 5. Here the figure A depicts the aluminum solid solution AlSi interdendritic pattern grains. The eutectic Mg2Si went into and appeared at primary aluminum's atomic surface, and many Al3Ni eutectics have a round structure here. Now the Chinese letter-like particles were absent here also. Now illuminated zones were recognized as aluminum actually. Now figure B depicts 200x magnification microstructure, which along with aluminum silicon has resolved grain boundaries and various precipitates. Now figure C actually shows the same higher magnification microstructure, that is of 500x. And it can be seen from the figure that the eutectics precipitated the resolved grain boundaries with aluminum silicon, Mg2Si and Al3Ni. Now also after 8 hours of solutionizing, the cast dendritic grains actually retained, and the eutectic particles of grain boundary were resolved, and the dark Mg2Si and Al3Ni faces were found to be finer in sizes. Okay, so that was the observation that we got from here. Now moving on to alloy 6. The aluminum silicon eutectic interdendritic pattern grains in a solid aluminum solution, that is shown in figure A. Now the eutectic Mg2Si dissolved and precipitated at primary aluminum's grain boundaries, and certain eutectics like Al3Ni have become rounded and are present in combination with aluminum silicon particles here. Now the Chinese script was absent in the microstructure, including eutectic particles. Now bright regions were identified as aluminum grains, and dendritic grains were fine, and segmented aluminum silicon particles are retained after casting. But higher temperature solutionizing effect is not pronounced here actually. Now figure B shows the microstructure at 200x, and which has a resolved grain boundaries. Now a few precipitated eutectic particles are also observed in primary solid solution grains of aluminum. Now here the figure C depicts the microstructure at a higher magnification, that is of 500x range. Now the grain boundaries here in figure C shows finer eutectic particles of Mg2Si and Al3Ni along with fine aluminum silicon particles. Now these aluminum silicon particles are dull, bright globular particles, and the effect of higher temperature modified the precipitated eutectic particles as round particles at the grain boundaries, as you can see from figure C. Okay. Now moving on to figure like microstructural observation in alloy 7, the figure A here depicts the aluminum silicon eutectic morphology in primary aluminum solid solution. Now they were less dendritic in shape, and the large dark areas are attributed to the precipitation of Mg2Si and Al3Ni particles during precipitation treatment. Now, however, the distribution of the strengthening eutectics was even larger in size here. Now, figure B here shows the magnified microstructure that is of 200x magnification, and it has resolved the grains, and the presence of large Al3Ni is resolved along with dark Mg2Si. Now, the figure C here shows the uniformly dispersed strengthening eutectics of Mg2Si and Al3Ni particles and as fine and large sized. Now, the light outlined particles, they are actually aluminum silicon, and which is rounded because of high temperature solution treatment. All right. So this much factors like facts we got from the microstructural observation actually. Now moving on to the next important phase, that was the mechanical properties of developed alloys. So as I said, I have studied my hardness, tensile strength, ductility, impact strength, and also fractography analysis that I have carried out. So first, I would like to talk about the hardness. So here this figure portrays the hardness variation of the developed alloys with respect to solutionizing temperature, as you can see. And it can be inferred from this figure that hardness was found to be 200 HV, that is because hardness for alloy solutionized at 550 degree, whereas for LM25 alloy it was 85 HV. Now improvement in hardness is actually because of the Al3Ni hard phase formation. Al3Ni is the intermediate phase that is forming here. Now this leads to the precipitation hardening, and because of this high cohesive force between the soft aluminum matrix and nickel. Now the present investigation was found to be in agreement with the study conducted before also, and it also confirmed that the aforementioned phenomena resisted the movement of aluminum under outside load. Now, thus it can be confirmed that the hardness of the developed alloys can be enhanced by increasing the solutionizing temperature actually. Okay, so that is regarding hardness. So we found an increasing trend for hardness from LM25 to 550 degrees Celsius solutionized alloy. The hardness ranged somewhere from between 85 HV to 200 HV actually. Okay. Now moving on to the next property, that is tensile property. So we have studied ultimate tensile strength, yield strength, as well as percentage elongation here. So here also first an increasing trend, that is for LM25 the UTS was found to be 109 MPa, and for 510 degrees Celsius solutionized alloy the UTS was found to be 330 degree. And then after that, a decline in the trend was seen, that is 265 for 530 degrees Celsius solutionized alloy. And then finally 22, a value of 22 for 550 degrees Celsius solutionized alloy. Now the same increasing and decreasing trend was observed for yield strength also, that is the green color shown here. So 38 we got for LM25, 45 for as cast, then 50 for 450 degrees Celsius, 80 for 480, 120 for 510, and 100 for 530, and finally 14 MPa for 550 degrees Celsius solutionized alloy. Now, clearly from this it can be seen that the value of UTS and yield strength that increases from LM25, that is the base alloy, to the alloys that is solutionized at 510 degrees Celsius. Now, this increasing trend in the present study that was found to be in accordance with the studies that was conducted before also for as cast aluminum alloys. Now the rise in ultimate tensile strength and yield strength with increasing solutionizing temperature, that is because of the hard Al3Ni intermediate phase that is formed here, and also due to precipitation hardening mechanism. Now, it can be seen from the figure that the value of ultimate tensile strength and yield strength decreases when the solutionizing temperature is further augmented to 550. And this decrease in the value of UTS and YS from 510 to 530, that is actually due to the reduction in vacancies causing formation of fewer aluminum nickel precipitates. And a further decrease in strength is owed to the formation of casting imperfections such as shrinkage, porosity, etc. that are observed during casting. Now, these results are found to be in terms with studies conducted by the previous literature also. The previous studies also confirm the same kind of trend in...
Sir, sorry for the interruption.
Yeah, sir.
Yeah, the decrement in hardness and strength could not be attributed to the casting defect. That could be possibly by the coarsening of the precipitate. The aging temperature is greater than 400 or 450 degrees Celsius. Then there could be a coarsening of precipitate. That might be the reason for reduction of hardness and strength. This is how I have read some of the literatures. But you mentioned about the temperature, aging temperature is increasing, solutionizing temperature increasing, and the casting defect could be the reason for reduction in hardness and strength.
That is also like that could be a reason, like reduction in vacancies causing the formation of fewer aluminum nickel precipitates, or mainly, as you said, rightly said, the coarsening. Yeah, mainly.
Yes.
So that can also
be could be the reason.
Yeah. Okay.
Thank you.
So this trend, okay. So this trend of increasing and decreasing that was seen, and the main reason for this increase was because of the presence of intermediate phase, that is Al3Ni, that was forming here. Now coming to the ductility investigation, the figure shows the different ductility values that we got for different solutionizing temperatures, and it can be seen from the figure that the value of ductility increased from 4.77% for LM25 to 10.8% as seen for modified compound that is treated at 510 degree. Now this increment is because of the spheroidization of eutectic silicon particles, and this restrained the split nucleation and opposed the plastic deformation actually. Now, the above results was found to be in agreement with the previous literature studies also for LM25 alloys. Now, a reduction in the ductility can also be observed in the figure as the solutionizing temperature is increased from 510 to 550 degree. Now, the decrease in the value of ductility from 510 to 530 is mainly because of the reduction in vacancies resulting in the formation of fewer aluminum nickel precipitates actually, and further decrease is attributed to the formation of defects in casting such as shrinkage, porosity, and inclusions as noted by previous studies. Okay, so previous studies have reported this casting defects as the reason for decrement. Okay. Now moving on, we have also carried out the fractography study here. Now the figure shows the fractured surfaces of aluminum, 6.6 silicon, 0.3 Mg, 3 nickel hypoeutectic alloy, exactly speaking, at varying solutionizing temperatures. Now this fractography was carried out using FESCM technique. The ductility trend here was also seen to be varying with an increase in the solutionizing temperature ranging from 450 to 550 degrees Celsius. Electron micrograph images of the samples revealed the dark round patched regions from where the secondary hard phase particles were removed when subjected to a tensile load. Now the micrograph revealed micro voids and dimples indicating the presence of both brittle as well as ductile phases in the fractured surface. Now the improvement in the ductility was evident from the observed micro voids in the fractography. Now the decreasing trend is observed with the increase in the solutionizing temperature after 510 degrees Celsius. And this was actually, this trend was actually attributed to the reduction in precipitate volume and the number of vacancies in the alloys. And this was actually reported by a previous literature paper also. Now from the figure, it is also very much evident that the specimen undertook marginal plastic deformation before the tensile loading. And this was validated from the presence of finer dimples observed in the micrographs. Now, a drastic decrease in the strength is observed here at a solutionizing temperature of 550 degrees Celsius. And this might be owing to the presence of innate casting imperfections like shrinkage, porosities, etc., which is evident from the micrograph that we obtained for fractography. So these were the results that we obtained for from the fractographic analysis part. So as I said, the decreasing trend is observed here with an increasing solutionizing temperature, and this was attributed to reduction in precipitate volume and number of vacancies in alloys, and this was reported before also. Now, yeah, as I said, the specimen has undertaken or undertook a marginal plastic deformation before the tensile loading has taken place. And this was validated from the presence of finer dimples that was observed in the micrograph. Okay. Now, decrease in the strength is observed at a solutionizing temperature of 550 degrees Celsius, and this might be owing to the presence of innate casting imperfections like shrinkage, porosities, etc., which is evident from the micrograph itself. Okay. Now, moving on, the next property that was studied here was regarding the impact resistance. Impact resistance. So this figure shows the impact resistance for the different alloy combinations studied, versus on x-axis we have given the solutionizing temperature. So it is seen that for LM25 it was for LM25 it was found to be 0.2 impact resistance, that is in joules, and then for as-cast condition it was 0.7. And then for 450 degree, it was 0.8. And then suddenly we got a rise of 1.2 for conditions 480 degrees Celsius and 510 degrees Celsius. And then afterwards, for 530 degrees Celsius, the impact resistance reduced to 0.9, and then further reduced to 0.7 for 550 degrees Celsius. Now, it is clear from this figure that the solutionizing temperature has a significant role to play in regulating the impact resistance of the developed hypoeutectic alloy or the developed alloys. Now, the impact resistance has been shown to increase by 14.3% and 71.43% relative to the as-cast state of aluminum 3 nickel compound when the solutionizing is set to 450 and 480 degree respectively. Now this increase in impact resistance is actually attributed to the development of Al3Ni layer and the hardening of the precipitation. Now further speaking, the decrease in impact resistance value is due to the reduction of vacancies resulting in the development of less aluminum nickel precipitates. Now, from the figure, it is verified that the optimum impact resistance value for the alloy is either 480 or 510 degree. So that is another finding that we could make out from this. That is the optimum impact resistance value for the alloy studied, that is aluminum, silicon, magnesium 3 nickel combination, is actually 480 or 510 degree Celsius. So that was another finding that we could make here. So that much regarding that was regarding the different property studies that we carried out in this study. That is I have described the microstructure, I have described hardness, then tensile strength, then ductility, and then now the impact resistance. All right, now moving on, I would like to conclude the main points or main findings in this study once again. Now, regarding microstructure, so in the microstructural analysis, we found that a refined grain structure is perceived as the solutionizing temperature is augmented or increased. Okay. Now, this XRD analysis conducted on the alloys, hypoeutectic alloys, confirmed the presence of silicon, aluminum, as well as Al3ni intermediate phases. Now, as there is a rise in the solutionizing temperature, the value of hardness was found to increase. And the increase in the value of hardness is because of Al3ni hard intermediate phases that was formed here, and also due to the precipitation hardening mechanism. Actually, we have the plan to study or analyze precipitation hardening mechanism in detail, but we could see that in India, the study to carry out precipitation hardening, like the equipments, the right equipment is not there in many of the places that we inquired. So that is why we had a practical difficulty in doing that precipitation hardening mechanism study. But still, we could make out the reason for this being precipitation hardening, as well as the Al3ni intermediate hard phase forming here. So this Al3ni intermediate phase can also be understood as a transitional stage that forms here, or a secondary stage we can call. Okay. Now, adding to these points, the precipitates the ultimate tensile strength, the yield strength, and the ductility, these three values of the developed alloys increased and reached a maximum value at 510 degrees Celsius, and then afterwards it decreased drastically to around 550 degrees Celsius. Now, the reason for this increase and decrease was attributed to the formation of hard intermediate Al3ni phase and precipitation strengthening mechanism. Now, the decrease in the value of ultimate tensile strength, yield strength, as well as ductility from 510 to 530 degrees Celsius, that was due to the reduction in porosity, resulting in decreased formation of aluminum and nickel phases, precipitates. And further decrease from 530 to 550 was because of the formation of shrinkage and porosity that were the usual casting defects formed during the casting process, as well as the coarsening of precipitates. Now, an increase in the impact strength, regarding impact strength, an increase in the impact strength was noted, and the solutionizing temperature was increased from 480 degrees Celsius to 510 degrees Celsius. And this increase in impact strength was because of the formation of hard intermediate, again Al3ni phase. Now, while the decrease in the impact strength from 510 degrees Celsius to 550 degrees Celsius, that was due to the reduction in the voids, which resulted in the formation of a fewer aluminum nickel precipitates actually. So that was the result that we got for the impact strength. So once again, the impact strength study showed that the solutionizing temperature was when it was increased from 80 to 510, the impact strength also increased. Now, the reason was being the formation of intermediate phase Al3ni here also, while the decrease in impact strength from 510 degrees to 550 degrees Celsius, that was due to the reduction in voids, which resulted in the formation of fewer aluminum nickel precipitates actually. Now, regarding the fractography study that was carried out as a part of the study, so fractography analysis confirmed the presence of both brittle as well as ductile phases in the fractured surface. So that was the single statement that we could make out from the entire fractographic study of this entire 7 alloys that was developed here. So this was a work which was carried out mainly at Amrita campus as well as Chennai campus. Then like this work took something around 8 months, 8 months to complete, and we took almost 2 months time to complete the paper, and fortunately we could publish this paper in Journal of Institution of Engineers, Springer publication, and that got published in 2001 February. Okay, so this was a recently published paper. So I just thought this topic would be of a great interest to the knowledge-seeking people sitting over there, and I hope this study, or the way in which the study was conducted, will help the people who have heard this presentation to carry out further research in this area and bring out further results and findings from their side. So adding 2-3 points to this. So solutionizing temperature influence was the point of focus in this research paper. So you can even study the effect of solutionizing time also. Solutionizing time over different solutionizing temperature conditions, and if you vary the solutionizing time, what would be the effect of microstructure, the changes in the microstructure, changes in the hardness values, then the properties like ultimate tensile strength, yield strength, as well as percentage elongation, then impact strength, then ductility. So solutionizing time, if you vary, you can even study the property variation that happens to all these properties also. So these were some of the references that I used here. There were something around 60, but I have quoted here something around 14 papers I have noted here. So all these papers were like gone into or looked into in depth, so that we could make out findings regarding microstructure as well as the other property relationships. So it was a cumbersome job, but by God's grace, the work I could finish like somewhat in the planned time itself. So that has taken up a lot of a number of my nights. So we have written it and got published it finally. And the precipitation strengthening mechanism, that was again a point of discussion that came up here. So we are actually thinking of doing this conducting precipitation mechanism study, even if it is outside India. So we are planning to also, but because of this pandemic situation that is right now, we are actually in a stuck situation. So once things get into normal and we get into the normal life, we'll be conducting that also. So then in my next paper, I would like to add that precipitation study mechanism also. Now, basically, this effect of different properties like hardness, microstructure, tensile strength, that is UTS, YS, as well as percentage elongation. So all these things were studied during my doctoral research time itself, and I have published almost 5-6 papers in that area. So you can just Google and find those papers. My name is Dr. Nidhin. Yeah. So related works are also I'm planning after. By God's grace, I think I'll be able to carry out those works according to my planning. So that's all for today. So I hope this presentation was helpful. If any questions are there, you can ask regarding this topic. So there are also many other aspects to be looked into this work. It is not a complete work actually. Actually speaking, no work is complete. No work is perfect. So you can always find demerits or shortcomings in any work. But to an extent, I hope I have done justice to this study. And still, there are many areas to be explored. So we have just focused on the solutionizing temperature influence using T6 in this particular 8356 alloy with 3% nickel. So yeah, with that I close my talk. So if any questions are there, you can ask. Hello, sir.
Yes, sir. Yes, sir. Participants,
Yes, sir.
do you have any queries? Do you want any discussion with the resource person? Now we
I think Pradeep Kumar have a question. Yeah.
Yes, sir. Thank you, Professor Nidhin. It's a very nice work and same the nice presentation as well.
Thank you, sir.
So I would like to ask a few questions. That is, first is, will you throw some light over process selections and process parameter selections over there? How did you select these kinds of parameters? And the second question was that how did you maintain the uniform distributions of these elements in these alloys? So can you explain, sir, please?
Yeah, I'll answer the second question first. So this uniform distribution of alloys, that was actually a point of worry for us from the initial stage itself. So we used graphite crucible actually with we even used the graphite tongs for the stirring purpose. So we from the morning we started the melting process, and I got the alloy something around evening 9 or 10, something around that. So we had to stir a lot because we also had to see that the magnesium does not vaporize this from this. So if the magnesium gets vaporized, means we'll not get the proper like property variation or and related things. So magnesium had to be kept at 0.4. So and we were fortunate to see after the spectroscopic analysis that the magnesium percentages was found to be somewhere around 0.2 to 0.4. So we had to keep the magnesium amount at 0.4% so that the precipitation hardening mechanism would be initiated in the system. Otherwise, if the magnesium is not there, means the precipitation mechanism might not initiate. Okay, so that will not like add up to an increment in the property and then a decrease in the properties, something like that. So in the precipitation hardening mechanism, as you know, you will have 3 phases. That is theta phase, theta dash phase, and theta double dash phase. So all these phases to appear means magnesium. The presence of magnesium is a mandatory thing. So that was our basic idea of concern, but and then the fluidity of like the metal, that would be increased. As I mentioned in the beginning of the talk itself, the silicon, the percentage of silicon, increased percentage of silicon, that would actually add to the increased fluidity of the entire system itself. So the nickel, dissolving of nickel was actually a point of concern, but because of continuous stirring we had to do. We had to take it every in an interval of 10 to 15 minutes, and then we had to stir it properly. We have to. I stirred it with my hand. So we had to stir it for a long time. So then only that the nickel will be completely dissolving in the alloy. So that was the point. And regarding parameters, yeah, we have. Yeah, parameters were selected based upon the literature study basically. So a detailed literature study was carried out well before the work was carried out.
Right, sir.
So from the literature only we took the parameters mainly. And it was also point of a concern to not to like do a work like similar to what was existing. So we had we have done like I added certain new elements also to the studies that were carried out already, and so T6 temper treatment, that was actually an added value to this work. So, and then we basically we decided the parameters from the literature study itself.
Okay, sir.
Participant, any questions? Any other queries?
Yes, sir. Good evening, sir.
Yeah, good evening, Vishwanath.
Sir, actually a small doubt. How I need to know what is the care taken by you to not to vaporize the magnesium in your alloy? What care did you take in handling the magnesium without vaporizing it?
Yeah. So that, as I said, that was the biggest worry that was worrying me through the entire casting thing. So we could only say, like, after we get the alloys, after we do the spectroscopic analysis, only we could say if magnesium is still there or not. So that was the situation actually there. Nothing like no other method we can adopt to see if the magnesium is still remaining, or if it has evaporated or not, like that. But in some cases, like, magnesium can evaporate. So in some papers, they have written clearly that magnesium can evaporate. So fortunately, in my work, the magnesium was there, and we got 0.2 to 0.4, somewhere in between 0.2 and 0.4. Magnesium was there. So like, finally we got a desired magnesium content in the thing actually.
Yeah. Yes, sir. Actually, we're referring some papers. They're saying magnesium can be evaporated. Please take care and this thing. So I need to know what care can be taken in order to not to have an evaporated stage of magnesium. So temperature should be limited, or any additives should be added. At what care have you taken specifically for magnesium?
No, we didn't take any specific step there anywhere somewhere out there. There was no mention of any such thing in previous literature. I referred the entire papers, and like, no such additional precautionary step to be carried out. I couldn't see anywhere. So we didn't add any additives or something like that. But we just did this thing very carefully, like stirring thing and all, very carefully. But yeah, like in one paper, or like I read it like that magnesium can evaporate. So but finally, in the arc spectroscopy, we could see that the content was there. From 0.2 to 0.4, magnesium was there in the alloy. So then I got happy, and like, then we proceeded actually. Otherwise, we would have had to do the entire melting process once again. So by God's grace, it was there. Magnesium was there.
Okay, sir. Okay, sir.
Okay.
Thanks.
Yeah. Any other questions? Thank you, sir. Thank you so much, sir. Thank you so much for the opportunity that was given to me